Welcome to M8307 Numerical Analysis class. In this lecture, we are going to introduce numerical integration. To determine the integral of f of x on some interval a to b, we usually find an analytical function f of x whose derivative is f of x. This is the antiderivative of f. And then take the difference between the values of this function at the limit points. However, there are many cases where this method doesn't work. For example, there isn't any analytical function corresponding to, for example, this integral. Okay, so we cannot find antiderivative of this function, or we cannot find antiderivative of this integrand. Similarly, the antiderivative of this function doesn't exist. Sometimes, even if we can find these functions, these antiderivatives, it may be convenient to take numerical integral. In the integral from a to b of f of x dx, instead of the function f of x, we can work with an approximation to f of x. Say this is g of x, for which taken integral is significantly simplified. Okay, so instead of working with f of x, instead of taking the integral of f, we take the integral of g of x, for which the taken integral is simplified. Okay, so we can basically write this approximation. So g of x is an approximation to f of x. As a result, the integral of f of x from a to b will be approximated by integral of g of x from a to b. Now the question is, how can we find this approximation function? To make the integral simpler, how can we find g of x function? We consider the function f of x on the interval a, b. We first ignore the parts in between, the a, b values. We can find polynomial that takes the same value with f of x at the end points. Okay, so the polynomial we need to find will be a line passing through the points a to f of a and b comma f of b. So this is the function value on the left end, and this is the function value at the right end. So we match these values with a line passing through these points, and this will give us an approximation to f of x. Okay, so say g1 is equal to f of a plus the slope times x minus a. So this is the linear approximation for the function f of x. If we rewrite this equation as in this form, so we can rewrite this equation in this form with some algebraic manipulation, then this will give us the approximation g of x. Here we observe something like here we have the function value at the left end point and function value at the right end point, and these two values, these two numbers, are multiplied by two polynomials. So this is the first polynomial and this is the second polynomial. So we basically multiply the function values with some polynomials, and we obtain an approximation. The last equation shows that we can find an approximation by multiplying the function values by some polynomials and then adding up. So this is something we observe. Okay, if we follow this idea and subdivide the interval AB as a is equal to x naught, which is less than x1, and this will go all the way up to xn, and xn will be equal to b. So we basically take subintervals of the interval AB. The similar approximation can be found by this formula. So g and x will be I from 1 to n. The function value at the node point, so these are the node points, function value at the node points times some polynomial Lix. So this is a polynomial. The unknown of this equation, unknowns of this equation are the polynomials Lix only, because we know the function f and we can find the value of function f at xi node points. Okay, so how can we find this Lix values, the polynomials? In addition to assumption that gnxi is equal to f of xi, so just in addition to assuming that the function values of the approximation and the original function match at the node points, we simply restrict this function to satisfy this extra condition. So we assume the Lixi value will be equal to 1, and also for any j not equal to I, Lixj is equal to 0. This is basically Li polynomials will take the value 1 if it is evaluated at the node point xi, and it will be equal to 0 if it is evaluated at the uh, node points other than xi. Thus, the polynomial Lix must take the value 1 at xi and 0 on the other node points. All these assumptions hold for the following polynomial. So Lix can be found in this way. So if we consider this polynomial, then these assumptions will hold, because for example, if we consider the point, if we substitute xi value here in this polynomial, then xi minus x naught will cancel with this term. So this will be xi, since we substitute xi for x. This two will cancel out, and also xi here, xi there, so this will cancel out, and all the terms will cancel out. This will cancel with that, this will cancel with that, and everything else will cancel out, so we'll end up with just 1. So Lixi will be equal to 1. If we consider xj, for example, and if we substitute xj here, j is not equal to I, then there will be some, because since we subtract all the xj values from x, if we substitute xj here, there will be some term x minus xj on the top, so this will make it 0, and multiplying anything with 0 will be equal to 0. So if we consider, for example, j is equal to 1, then x1 will enter here, so x1 minus x1 will be equal to 0. Even if we have other terms are non-zero, this 0 factor will make the polynomial equal to 0. If we consider, for example, j is equal to I minus 1, then when we substitute xi minus 1 here, this term will cancel out, this term will be this will be 0, so this being 0 makes the polynomial equal to 0. So seems like this polynomial will satisfy our assumptions, like the function value at xi will be equal to 1, and the function value at xj, j is not equal to I, will be equal to 0, basically. Okay, we can rewrite this polynomial as in this form, so as a product notation. So j is from 0 to n. If j is not also j is not equal to I, the product of all this linear polynomials. Thus, we have found an interpolation for g of g and x, because we were interested in finding an approximation in this form. So we said we know this part, and also Lix is found in this way, so we also know this part. So this gives us the approximation g and x function, because we know all the unknowns now. Okay, so this g and x will be an approximation function to f of x on the interval ab. So this is a significant result for much more than a numerical integral, because this is an interpolation, and we use this interpolation pretty much everywhere in the numerical analysis. Okay, a remark. One can find an interpolation function using numerical values collected on a field trip. Okay, so you're an engineer, you go to a field trip and collect some data. So you can use this data values to obtain an interpolation function corresponding to that data values. This interpolation is a way to construct an analytical function that complies with the given data. So this interpolation will give us a function that give us an analytical function, and this analytical function will comply with the given data. Okay, an example: 3-month groundwater levels are given in this table. So this is the table. In the first month, in the beginning, we have 0.7, and at the end of the first month it will be 1.5, and then in the second month it will be 1.4, and in the third month it will be 1.2. So this is the table. We are given this groundwater levels at a given time, and we can use an interpolation polynomial to approximate the data values here. So we basically use this idea. Okay, so we have given the function values, the data values in the table, and we can use the polynomial here. This is also known as Lagrange interpolation polynomial, and we can use this Lagrange interpolation polynomials to obtain an approximation to the given data. So this will be our approximation interpolation polynomial, and then we can use this interpolation polynomial to, for example, estimate the groundwater level at the coming month. Okay, so the water level at the 4th month is not given here, but we can estimate the water level as 0.7 by simply using this approximation. So this is another application of the interpolation polynomials. Okay, if we go back to the numerical integration, since we have f of x is approximated by this polynomial, this function, then we can rewrite this integral as an approximation by this formulation, like we substitute f of x here. Okay, so this will be from a to b of integral of the approximation, and we observe that the function values at the points are just numbers, and this sum is finite. So we can take this sum and the function values out of integral. So this is something we are allowed to do. Okay, when we do that, we see this part is known and this is just sum. So integral is only at the interpolation polynomial. So the integral will happen on the Lagrange interpolation polynomials. Okay, so this gives us an immediate consequence, because no matter which f values we have, this integral will be the same. Okay, so if we have the same data points, if you're working on the same data set, this integral will be the same all the time. So we can use this information to take integral of any function, not just f. If we are given, for example, some other function, we can still do the same. Okay, so if we let this this integral, be equal to wi, the weight, then this will be equal to, this will give us this integral will be equal to basically wi times f of xi. So it seems like to find the integral of the f function numerically, we basically take the function value at the node point, and then we multiply that by a constant. Okay, so we do that, and then we add them up. The result will give us the numerical integral for this analytical integral. Okay, so wi values can be computed beforehand for any given data set, just like I told you before. So if you're given the same data set, xi values, then we can compute wi values for this data set, and then once we obtain their values, the equation 1 will give us numerical integration for any given function. Okay, so we can change the function f to, for example, h, and this will still give us an integral. So what we really need to find is just this wi values for any given data set. Okay, in particular, if we let the subdivision of this AB interval is equidistant, is a set of equidistant nodes, then we say A is equal to x naught, x1, xn is equal to b, and their equidistant and distance will be delta x. So we say we have n plus 1 node points, so delta x will be basically b minus a divided by n, and the distance between any two node points will be delta x. So basically we say x1 is equal to x0 plus delta x, or for example xn is equal to xn minus 1 plus delta x. So we can in general write this for xk, and xk will be equal to a plus k times delta x, because we move k times delta x from a to obtain xk. Okay, denoting the vector w as wi, the components of the vector v as wi. Its values for various methods can be found as, for this particular data set, in this definition. So rectangle rule will be in this form. So w's will be either delta t times 0 for w0 and 1 for w1, and it will go all the way up to wn as 1. And also here some other formulation for rectangle rule will be delta t again for w1, and w2 will be delta t, and wn minus 1 will be delta t, and wm will be equal to 0. So these are two options for rectangle rule. And for the trapezoid rule, we see w is equal to delta t over 2 times this vector. So this will be w0, w1, w2, and so on. So these are the weights, wi values for trapezoid rule. And Simpson's 1/3 rule will be in this form, so we can obtain wi values using this vector. And also Simpson 3/8 rule will be in this form, so the weights will be as in this vector. Okay, so here we also observe that this will start with 1, and there's a pattern here: 1 4 2 4 2 4 2, and it will end with 4 1. Okay, and in this formulation also we have 1 3 3 2 3 3 2 3 3 2, and it will go all the way up to 3 3 1, and this will end this has to end with this term, and this numbers and that numbers in between we have 2's. Okay, for the rectangle rule, calculations of the integral with the first coefficient is called the right rectangles rule, and with the second coefficient is called the left rectangle rule. So if we consider take an integral of some function, and say we use rectangles to approximate their the integral of this function. Okay, so say these are the rectangles we use. Then depending on which points we use for the function values, we observe we call the we name the rectangle rule with this observation. So we have, for example, here we use the left end for the computing the numerical integral, and here again left end. So this will be left rectangle rule. And if we instead use, for example, the right ends, like here, so this is the right end, and here we also have used the right end for the function. Okay, function values. If we use, for example, this point, the right end points for the function values, then this will give us the right rectangle rule. Okay, so this is something we can immediately observe. Or if we use, for example, a trapezoid to compute integral, so say this is the trapezoid we use, so this is the trapezoid we use to find the integral, then this will be our trapezoid rule and it will correspond to that weights. Okay, remark: to apply Simpson's 1/3 and 3/8 rules, n must be divisible by 2 and 3 respectively. Okay, so in order to use Simpson's 1/3 rule, it has to be divisible by 2, and for 3/8 rule, it has to be, the number n has to be divisible by 3. So otherwise this pattern, we cannot apply this pattern. Okay, so this is all about applying this pattern or not. Okay, for some C in AB, the interval AB, the expected error with these methods are given in this table. So with the rectangle rule, the error will be b minus a divided by 2 times the first derivative of f at some point c times delta x. What we care about here is this delta x, because all the other terms will be constant. Okay, so this is just first order approximation, because if we take the half of delta x, the error will be halved. And also we say the rectangle rule will be exact for polynomials of degree 1. So it will be exact for constant polynomials. Okay, the trapezoid rule. For the trapezoid rule, error will be in this form. So again, this part will be just a constant. If we assume it's the function f is twice differentiable and bounded, the second derivative is bounded on AB, then this is just a constant, and delta x will be the part that gives us the order. So since we have 2 here, this will be second order method. Okay, so if we take the half of delta x, then the error will be 1/4. Okay, so trapezoid rule will be exact for polynomials of degree 1. So trapezoid rule will be exact for linear polynomials. Okay, Simpson's 1/3 and 3/8 rules are fourth order approximations. Okay, so they are fourth order and they will be exact for cubic polynomials. Okay, so they will be exact for polynomials of degree 3. Okay, an example: approximate the integral from 0 to 3 of x cubed dx with the given rules for n is equal to 6, and then compute errors. So n is 6, so in order to find delta x, we take the difference between the endpoints. 3 minus 0 divided by 6 will give us delta x, so the delta x will be equal to 1/2. So our 6 node points will be 0, 1/2, 1, 3/2, 2, 5/2, and 3. So this will be our data set. And first we need to find the function values at these node points in order to find the numerical integral, because we need the function values at this node point. So let's put them on a table. So for x is equal to 0, the function value will be 0, and x is equal to 1/2, function value will be 1/8, and it will be, we can compute the rest using this formulation again. Okay, so this is the function values. For example, if we consider the right rectangle rule, the weights for right rectangle rule is 0, 1, 1, 1, 1, and it will go all the way up to n, like 1. So this gives us 0 times the function value at the first node, which is 0, and 1 times the function value at the second node, which is 1/8, and so on. So we basically multiply weight with the function value at the corresponding node and then sum them up. The result will be equal to 27.5425. So what is the error? We can simply take the integral of this function. The integral of this function will be x to the 4 divided by 4, If we substitute 3 for the endpoint, it will be 81 divided by 4, which is equal to 20.25. So this is simple enough to find. If we find the error using this the exact result of the integral, we observe that the error is equal to error is around 7. Okay, so this is right rectangle rule. If we consider left rectangle rule, the weights for left rectangle rule will be 1, 1, 1, and it will go all the way up to xn as 1, and at the xn it will be equal to 0. Okay, so if we apply this formulation and multiply each weight with the function values, we obtain this result. And here the error will be equal to 6.1875. Okay, so this is still error, and it is quite high because n is not large enough, just 6. Okay, if we consider trapezoid rule, here we again in the formulation we have delta t squared times 1, 2, 2, 2 for the base 2, and it will go all the way up to wn. In the wn it will be equal to 1. Okay, so if we compute this numerical integral, it will be equal to 20.8125, and then the error will be equal to 0.5625. If you consider this, if you compare this error with the error of the rectangle rules, this is significantly low. Okay, so this is because trapezoid rule will give us much better approximations than the rectangle rule. Okay, what about the Simpson 1/3 rule? Okay, with the Simpson 1/3 rule, we have let's go back to weights again. So here we have the weights are delta t over 3 times 1, 4, 2, 4, 2, and it will go all the way up to wn as 1. So here delta t is equal to 1 over 2 in our case, and this will be 1 over 6 times the weights. Okay, let's go there. So 1 over 6 times 1, 4, 2, 4, 2, 4, and it will be 1 for the last node point. And if you perform this computation, this will be 20.25, and the error with this computation will be equal to 0. Okay, and also with the Simpson 3/8 rule, we again apply the same formulation. Here in the table we have 3 delta t over 8, so delta t is equal to 1/2 in our case, so this will be 3 over 16 times 1, 3, 3, 2, 3, 3, and so on. So we have 3 over 16 times 1, 3, 3, 2, 3, 3, 1. Okay, so if we substitute function values in their corresponding parts and compute this integral, this will be equal to 20.25, and we see the error is equal to 0 again. Okay, why is that so? Why do we have 0 error with this function? Because we already mentioned once here for Simpson's rule, the polynomials of degree up to 3 will give us exact value for the integral. Since we're working with a cubic polynomial, we already expect to get exact value for the integral. Okay, this is something we already expect. But if we, for example, consider x to the 4th here, then this Simpson's rules will not be exact anymore, so we will obtain some error not equal to 0. Okay, that will conclude our lecture here. Thanks for watching carefully. Bye.